All right, so welcome back. We're going to go ahead and take a look at pages 3 and 4 of our final exam review. If you hear a few voices of the background, I've got some students in here working on a project, but I don't think it'll be too much of a distraction. But here we go. So page 3, this is kind of a blast from the past, talking about triangle congruence, which is something that we really stressed a lot first semester, but not nearly so much second semester. You want to remember that we had side, side, side. We had side, angle, side. We had angle, angle, side. We had hypotenuse. Like we had all of these things that we liked. But remember, we didn't like ASS or SSA. And we also didn't like AAA as well. If you only get angles, that's not good because that's really about similarity. So let's see what we got. So in this particular problem, this is angle ADB. Remember, tracing ADB, that would be this angle right here. It says it matches CBD, where, remember that center value is always going to be the vertex. CBD would be this guy right here. It also says that angle ABD, now that's a little bit different. Angle ABD, that would be this angle up top, is the same as CDB, that's this guy down here. And so notice that I have two angles on the top triangle as well as two on the bottom, which means we are going to be looking at an ASA congruence story. I guess I missed that in my little list. And so again, one of the things that I like about these problems, or I liked when I was a student, is that sometimes there's a hint. This was actually named very well. Triangle A to D to B should be the same as triangle CBD. See, if you have actually named it well, it should make sense. A to B to D. So unmarked to the double, angle over to the single, unmarked to the double to the single, CDB. Good. Now here, again, it says AB right here, congruent to CD. This is AD over here, congruent to CB. And of course, this side is the same as itself, just like the previous question. So it looks like we got side, side, side congruence. And this time we don't quite have the fortune that somebody named them all for us, but that's all right. We can still do it. So I'm just going to name it BAD. BAD congruent to. So BAD, so as I trace it, it's going across the single to the double. So the only way I can trace the single to the double would be DCB. Now, for number 13 here, this is kind of important, and I want to go slow on this, is that you could probably look at it through proportional reasoning and see that there's this little 2-to-1 ratio, but we really should be thorough about that. We should say the ratio of 12 to 6 is the same as the ratio of 8 to 4, which is the same as the ratio of 7 to 3.5, which every single time is like this 2-to-1 ratio. So remember, you've got like the 12, you're saying corresponds to the 6. We're saying the 8 here corresponds to the 4. We're saying that the 7 and the 3.5 kind of match up. That's pretty nice. And so I would say that that would be that triangle ACB would be similar to triangle. So notice ACB, I went across pink and then orange, so it'd be XZY. Now that would probably bug some of you because it's not alphabetical, but I just named it the way I saw it immediately. And I could say that that was by side, 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 but not congruence. It was similarity because all three proportional sides. And in fact, when you say this, that's what you're implying. Now, going a little bit further, if we have angle A right here the same as angle X, and angle C right here the same as angle Z, the 5 and the 20 are completely irrelevant pieces of information because all it takes to show similarity is two angles. And so again, I think I will say triangle ACB similar to, so ACB would be single, double, unmarked, so it'd be XCY. And we're done with that one. Now, it is a 4-to-1 ratio, but we actually didn't have any need of that piece of data. All right, let's move on to our last page, okay, for this particular video. Here we go. Now, the big bad proof, this is what everybody always gets worried about. So keep in mind, the first step to every proof is understanding all the givens. So it says that JK here is parallel to MN. Now, so JK here is parallel to MN. Now, please understand that said they are parallel. It does not say they are congruent. Please be clear. I can have stories like this that intersect like that, where one triangle is much smaller than the other triangle. It happens all the time. Please do not believe that parallel and congruence are automatic. They're not. But that was given, as well as the fact that Jn bisects Km. Remember, the first step to every proof is that given information. But now we're going to go ahead and start using that information. So why do I know that angle MNL is the same as KJL right here? That would be true because alternate interior angles of parallel lines are congruent. Sorry about my like penmanship. But if lines are parallel, then alternate interior angles are going to be congruent. Now, there's a little something that we said right here that says Jn bisects. Now, that's a fancy word, and so we always want to go ahead and utilize that definition of that fancy word. So it says Jn right here. Jn bisects Km. That means Jn is like the knife that cuts this one. That means these two segments, which would be ML, would be congruent to KL by the definition of that bisector. Okay. Now we're looking pretty good. We got an angle and a side. That's not enough. Remember, we need a little more. We need either another angle or another side or something. But this is a case where you really have more than one option. There's really two that we could use. We could use alternate interior angles again, but I wanted to go ahead and use the fact that these two angles right here are the same because the vertical angle theorem says so. And the vertical angle theorem simply says vertical angles are congruent. So everybody has their own way of doing this, but I'm going to go ahead and say angle JLK is the same as NLM by the vertical angle theorem. And now what we have is two angles and a non-included side, and we're done. Okay, we're getting there. Number 15 through 17 to go, and then we'll be done with this video. So keep in mind, this is a quadrilateral. And most recently, we had that quadrilateral in a circle, but that's not what we have. It is just a quadrilateral. So we should know that all of these things should add up to exactly 360 degrees. So I got 5 x's, I got 5 more x's, so I got up to 10. 4 more makes 14, plus 3 more makes 17 x's. I got 16, but I lost 15, so I'm down to 1. Plus 36 makes 37. So there we go. I just did a little combination of like terms. That's going to be 323. And now we just have to do a quick division and find out what happens if we take 323. Let's just double check something. 360 minus 37. Yep, divided by 17. And I found out that x is 19. Now, we always want to look back and make sure. Oh, it did say just find the value of x. On the test, it might say what is the value of angle A, and then I need to plug it back in. Okay. Now, 16, I'm a little bit concerned about because I know that a lot of people aren't going to remember this little fact, but a rhombus has all of these sides are the same. But when that happens, when you draw your diagonals in, they always intersect at 90s. That's a fact that is always true for rhombi. The diagonals are always perpendicular and they bisect each other. So you have to know those two facts. So it says one of the diagonals is 10. So I'm going to make both of these 5 because they bisect each other. This is 24, so I'm going to make them both 12 because, again, the diagonals bisect each other. But since this central angle here is a 90, then of course I can use the Pythagorean theorem and say that a squared plus b squared equals c squared. And that's 25 and 144, which of course is a pretty nice number, 169. That makes each side here 13. And it didn't ask for the side length, it asked for the entire perimeter. So my perimeter would be 13 times 4, which of course is 52. So give me 1 second here. I'll be right back. All right, one last question. We're going to go ahead and look at our parallelogram. Here we go. So our last problem is that we have a parallelogram. Now, what is different about parallelograms, although this is a rhombus, which truly makes it a parallelogram, but it was special, the only difference is these aren't perpendicular. So I know that the distance from A to P is the same as the distance from P to C. And I also know the distance from D to P is the same as this one. So what they asked me to do in this problem is go through that and find the length of the diagonal. So that's one of the things that I mentioned earlier. Please don't just try to find the value of the variable. Go that one extra mile. So we're going to go ahead and take AP, and I'm going to set that equal to PC. And so if we do a little bit of movement of our x's and our constants around, I found out that x is 15, of course. But then we're going to want to go ahead and plug that in. So 2 times 15, of course, would be 30, plus the 25 that is sitting there is 55. So I found that both of these values are 55. So the diagonal from A to C, because notice it says the length of the diagonal, all the way from A to C would be 110. And what's really important to me is if you just say AC with no segment, nothing attached to it, you are saying the length of the segment from A to C is 110. You don't have to explain it as long as you do 2 capital letters side by side. Similarly, you have y plus 7 being 3y minus 11. That's going to give us 2y is 18 or y is 9. Sorry if that was too fast. But y plus 7, of course, is 16. So I know both of these pieces are 16, which makes the segment from D to P, oh, D to B, actually, D to B, right here, a total of 32. And we're done. All right. Pages 3 and 4 are done. I will see you guys back in class. Bye-bye.